Hey, welcome to the Actuarial Data Scientists. By the end of this video, we'll know how to determine the minimum variance unbiased estimator. Let's get started. So I decided from now on to not read the problems to you. I'm guessing most of you are just skipping over it. So I'll be sure to pause momentarily. Feel free to pause the video and read the problem yourself if you need to. Otherwise, I'm assuming most of you are finding these videos through search, and so you're stuck on a problem or you're already aware of what the problem is. So with that in mind, we're just going to jump right into it. Really, for this problem, all you need to know is minimum variance unbiased estimator. And by all you need to know, I mean it's got a lot of moving parts. And really, I was able to get the solution on an early attempt, primarily just because I knew what the variance for normal was when you know mu. Just I couldn't remember why I knew it, and that definitely made this problem a lot easier. But to actually go through the steps of solving for it is fairly complicated, so we're going to go through that here. So overarching topic that you need to know is the MVUE, minimum variance unbiased estimator, is just an estimator that is both unbiased, and there is no other unbiased estimator which has less variance. So you essentially have found the optimal estimator that is restricted to being unbiased. So with that said, that's kind of the goal. Going into the tools you kind of need to know in order to determine that, first is sufficient statistic. So this is a direct quote from Wikipedia, just because they got the wording nice, so I thought I wouldn't try to reword it. A statistic t of x is sufficient for an underlying parameter of theta, precisely if the conditional probability distribution of the data x, given the statistic of t of x, does not depend on the parameter theta. So I'm actually going to move forward into the Fisher-Neyman factorization theorem, which is getting at what I feel like is the same thing. So for a PDF, so f of x, given some parameter of interest theta, you can rewrite the PDF as being the composite of two functions, or the product of two functions. So you have some function h of x, which does not depend on theta, and then you have a separate function which is dependent on theta and x. And the goal is pull as much of the PDF into just h of x, because you can then ignore h of x, and then whatever components of x are in that g function are your sufficient statistics. So I found this to be not super intuitive, and I don't like dealing with the raw PDF. So this is the theorem that is used, but I prefer to go from the more intuitive maximum likelihood, which I'm not sure if this is exactly what Fisher-Neyman's factorization theorem is. I think it might be, but this is how I think about it. So most of this I directly copied from Spring 2019 question 15, I think, where I walk through maximum likelihood estimation. So for now, I'd say just kind of ignore most of this wording, but feel free to pause and read through it if you'd prefer. But the maximum likelihood is just when you say, given some hyperparameter value alpha, I pick what the hyperparameter is. What's the probability then of seeing the data that I saw? And so the maximum likelihood estimator is saying, well, what's the likelihood of seeing that given your selection of alpha? And then what selection of alpha can I pick that maximizes that likelihood? So we can do the product of the PDFs, and that's what this pi symbol here, capital pi, is. It's the product. We then want to find the maximum. So a monotonic transformation, just taking the natural log, will not change the location, what x will maximize that function. So essentially, we're not changing anything of importance by taking the natural log, but we do that because it makes taking derivatives a lot easier. So here we see the natural log of that product just becomes the summation of the natural logs, shown here. And then we can get into more of the specifics. So that's where it stopped for that previous question we already walked through, spring 2019, question 15. But here we can then say, okay, at this point we would take the derivative and set it equal to 0. But what you can do is, since they're natural logs, if you write them in this form of just dependent on x and then dependent on some combination of theta and x's, you can then break them apart. So the natural log of their product is going to be equal to the natural log of h of x plus the natural log of that g of t of x. And then what happens is you take the derivative with respect to theta, and you see that if you have this value, which is only dependent on x, and you take the derivative with respect to theta, then that just goes to 0. Whereas if they're somehow intermingled with each other, then you have to actually take the derivative. So I feel like you had to kind of follow along for quite some time for this to come full circle, but going back to this sufficient statistic, this is how I think about sufficient statistics. You're looking at the maximum likelihood and how you would go about getting that estimate, and you're saying, what about x do I need to know to have sufficient information to create a maximum likelihood estimate? And the reason why it's sufficient is because, hey, there is this additional information about x, right? This h of x, but g of x is sufficient. And the reason for that is h of x derivative with respect to theta is just going to go to 0, and so we can ignore it. So that's what ties the sufficient statistic to looking at the derivative, the natural log of the or the log likelihood, and that also ties into this theorem here of Fisher-Neyman's factorization theorem. So that's all this is getting at, is h of x, when you take that log, just is going to go away. Okay, so it's a lot of rambling, but so there's that. So at this point, we now know how to find the sufficient statistic. So that's where we're at right now. The next step is to know Rao-Blackwell. So again, I have a lot of writing here, and that was mainly because this was actually a pretty tough problem for me to get a really good understanding of these foundational principles you need to know. And so these are to help me kind of go along, so I'd recommend you either just listen to me talk or pause and read. Trying to do both will be a nightmare. So at this point we say, okay, if I have some estimator, in this case we're calling it g of t of x, so an estimator using the sufficient statistic in some capacity, although it doesn't need to. We have some estimator. What can we do to improve the estimator? And one thing we can do is condition on the sufficient statistic to see if it brings any additional information. So using the law of total expectation and the law of total variance, we get a few things. So first off, we have some estimator g of t of x. If we then take the expected value of g of t of x given the sufficient statistic, and that's our new estimator, right? Well, what's the expected value of that new estimator? And that's why we have these double expectations. And we end up getting just right back to our initial thing. So we have the expected value of the expected value of something given something else. Well, we can then just ignore this given. And so what this is saying is, if our initial estimator is biased, then our updated estimator conditioning on the sufficient statistic is also biased. Likewise, if it was unbiased, it will stay unbiased. So that's all this is saying, is by conditioning on t of x and then taking the expected value of that overall value here, we're not going to be changing that expected value. Now the second thing that we're going to get is that the variance of our original estimator is going to equal the sum of these two quantities. Our updated estimator is just this, the expected value of g of t of x given sufficient statistic. And so we then can look at the second component, this expected value, and say, well, it's the expected value of some variance, and I know variance is greater than or equal to 0. So we have old variance equals new variance plus some non-negative number. And so given that, we can then say, okay, I know for a fact that my new estimator is going to have the same variance or a smaller variance. So that's what we're getting here. So at this point, what we then can say is, so one thing I chose to do was say our current estimator is g of t of x. So I'm hinting at our initial estimator is going to use the sufficient statistic, but that's not necessarily the case. When you do then condition on the sufficient statistic, it is very likely that your variance is going to be reduced. You're going to end up getting a better estimator. However, if you already are using the sufficient statistic and then you condition on the sufficient statistic, it's not going to get any better because you're not bringing any new information to the table. Finally, you can also condition on something other than the sufficient statistic. So I chose to be talking about that because that's what's relevant to us, but you could condition on anything, and all this would still hold true. However, if you condition on anything other than the sufficient statistic, by definition, it brings no additional value, right? Anything other than the sufficient statistic doesn't give us any new information. And so what that means is it's going to guarantee the variance is unchanged. So, I have an estimator that has some variance, and then I tell you, oh, I have a YouTube channel called the Actuarial Data Scientist. Great, that's no new information to me. That is relevant to my parameter estimates, so my variance is unchanged. So that's how this could still, I think, relate to unnecessary information. And then if you're conditioning on the sufficient statistic, it's going to either make it better or stay the same. So with all that said, when you use the sufficient statistic, the variance is optimal. And then also, if your initial estimator is unbiased, it will still be unbiased. So we now know that we have an unbiased estimator that can't be reduced because conditioning on anything else won't make it any better. And so if you are able to find an unbiased estimator that uses the sufficient statistic, then you know you have the minimum variance unbiased estimator. So that was a lot. Alright, so yeah, I have it right here. So in summary, that was still high level. I didn't do any formal proofs. So feel free to do that on your own. I tried to, and that's the level of depth that I felt comfortable going into. But in summary, what you need to know for this problem is that given a sufficient statistic, creating an estimator using that is unbiased will be the minimum variance unbiased estimator. So this won't necessarily always be possible, but if you're able to do so, you have found the minimum variance unbiased estimator. So now what we can do is go to the actual problem. So we have the normal distribution. You can look up the PDF for that using your formula sheet that you're provided. And we can then right off the bat simplify because we know that mu is 0. So that's given within the problem. So this mu just goes to 0. And then we find the sufficient statistic. So here we're going through the steps, converting to the sum of the natural log of the PDFs, then breaking it up into its components because the natural log of a times b is equal to the natural log of a plus the natural log of b. So that's what we're doing here. Breaking things up. So from here, we then take the derivative with respect to our parameter of interest, which is sigma. And that is how we get this quantity. And then that just goes to 0, this constant on the right. And then what we do is we multiply both sides by sigma, so this sigma cubed becomes sigma squared, this sigma goes away, and then 0 stays 0. Finally we simplify and we get that our maximum likelihood estimator is going to be the summation of x squareds divided by n, and that's our estimator. So at this point, maximum likelihood estimators are not guaranteed to be unbiased, and we have been tasked with finding the minimum variance unbiased estimator. So what we need to do is check that it's unbiased. So we just need to know what's the expected value of this quantity, the sum of x squareds divided by n, and see if that is equal to sigma squared. So again, we know that mu equals 0, and we know our variance formula. And since mu is 0, the expected value of x is 0. So the expected value of x squared minus 0 squared is just going to be equal to the expected value of x squared. So now we look at the expected value of our estimator. That's just equal to the summation of the expected value of x squareds. And so we end up with n over n times sigma squared, which is just sigma squared. So we have shown that it is unbiased and that we can calculate it using the sufficient statistic. So at that point we know we found the minimum variance unbiased estimator, and all we need to do is then plug and chug. So we know the sum of x squareds is equal to 500, and our sample size is 10, and so our final answer is not 10, that's a typo, it is 50. 500 divided by 10 is 50. So scrolling back up, we see that that falls in the range of C, so that's our final answer. Thanks for watching. As always, please consider liking, subscribing, doing all that good stuff. And if you like a good stats pun, started selling merch, because why not? Everyone else is doing it, so feel free to check that out as well. Thanks. Have a good one.